Now that I've described the analysis types available in HEC-SSP, let's create and compute an analysis. I'm selecting Analysis New, Bulletin 17 Analysis to open the Bulletin 17 editor. I want to compute a Bulletin 17C analysis using the Bushkill at Shoemaker's annual peak flow dataset. So I'll enter Bushkill B17C as the analysis name. I can enter a description if I want to, and now I'll select the dataset from the drop-down menu. Notice that there are only 2 datasets available, and that's because these 2 datasets have an irregular century time interval. As I mentioned before, data must have an irregular century time interval to be selectable in this type of analysis, and the dataset must contain one and only one annual peak in each water year. Now I can modify my options in the various tabs. I'm going to leave the default of 17C EMA for my computational method, and I'll leave the default of use station skew. I'm not going to compute expected probability, and if you're interested in learning more about this topic, we have an entire webinar on this YouTube page dedicated to it. The selections in the middle column are based on my selection of 17C EMA. I can modify the confidence limits and the time window if I want to. Next, I'll move to the Options tab. On the Options tab, you can override the low outlier threshold value and compute variable time window options. After this analysis, I'll come back and demonstrate the 3 options in the variable time window. The middle column is used for Bulletin 17B procedures, and in the right column, you can modify the frequency ordinates. On the EMA tab, you can add information about sensor data and historical data. This gauge has 115 systematic peaks, or peak flows that were measured by a streamflow gauge, so we don't have to enter any censored or historical information for this site. Next, I'll go to the NEB tab. This is where you would enter paleoflood information, such as a non-exceedance bound or paleostage indicator. Now that I've entered all my data, I can compute the Bulletin 17C analysis. The top table shows my frequency curve, including my confidence limits. The lower left table shows my distribution parameters. If I had entered regional skew information, I would see that value in this cell and a weighted skew below it. The lower right table gives me an event count and information about the types of events. As I mentioned before, we have 115 systematic annual peak flows and no additional information. I can also plot my frequency curve and edit the plot properties like I showed you before. I can hide this panel by right-clicking and selecting Hide. If you want to see more detailed information, click View Report. Now let's duplicate our Bulletin 17 analysis and look at the variable time window options. To duplicate an analysis, right-click on it and select Save As. I'll change the name to Bushkill Variable Window. On the Options tab, under the Variable Time Window panel, you have 3 options. The default is to not compute using a variable time window. Let's change that to use a moving window. This will compute your flow quantiles and distribution statistics using a uniform window length, but shift that window by a shift increment. The default is 1 year, but I'm going to change that to 5 years. Now I'm going to recompute. The Variable Time Window Results tab is now enabled. You can examine how your frequency quantiles change as you use a different 20-year period using this table or the corresponding plot. Notice that all of our flow quantiles increased dramatically after the flood of record in 1955, but then decrease as we shift beyond that flood of record. You can also see that in the tabular results. You can pop plots out of any editor in SSP by double left-clicking in the gray area. We can also look at how our distribution statistics change through time. You can see that in the table and also in the plots. Notice that our station skew is very sensitive to which 20-year period of data that we're using. This is why we often incorporate regional skew in order to stabilize our at-site estimate. Let's go back and change this to an expanding window. The initial number of events is the number of years of data that the first computation will use. We then need to specify an expansion increment. The default is 1 year, but I will change that to 5. This means that SSP will compute the first evaluation using 20 years of data, the second one using 25, the third one using 30, and so on and so forth, until it uses all 115 annual peak values. Like before, I can look at how the flow frequency quantiles change as a result of our expanding time window. Again, our frequency quantiles jump dramatically after the flood of record, but then they decrease as we incorporate more annual peak flow. We can also look at the statistics information. Notice that there is an asterisk next to my study name. This indicates that there is an unsaved analysis in the study. I can save by clicking Control-S on my keyboard or the floppy disk button. For the last part of the demo, I'm going to create and compute a duration analysis. This time I'll create a new analysis by right-clicking on the analysis node and selecting New. I'm going to use Blue River as the name of my analysis. And from the drop-down menu, I'll select the reservoir elevation dataset. Only regular time interval datasets are selectable in the duration analysis. I'll leave the defaults for the method, x-axis scale, and y-axis scale, and I'll also leave the full time window of my dataset. I want to enter user-defined period, so I'll select that from the drop-down menu. I'm going to divide my time series into 5 time periods in order to compute separate duration curves for each. On the Options tab, I can change my output labeling, my plotting position formula, and choose whether I want to plot an interpolated curve or not. I can also change the output frequency ordinates, as I could in the Bulletin 17 analysis. The bin limits options are modifiable if you select the bin method on the General tab. I can now compute my duration curves. I can see tabular results on the Results tab, and I can plot my duration curves. Notice that each user-defined period has 2 curves, interpolated and computed. I can select an item in the legend to highlight it in the plot. Our duration curves are drastically different between the fall and winter and early summer months. For example, a reservoir stage of approximately 1350 feet has a 50% chance of being exceeded in the month of June. But this stage drops to about 1208 in the November through February time period. This concludes the demonstration portion of this lecture.